British Airways Airbus A320 narrowly avoids disaster aboard London after mid-air stall during Heathrow approach. A routine British Airways flight from Germany to the United Kingdom reportedly turned into a serious aviation emergency after an Airbus A320 experienced a dangerous loss of control while approaching London Heathrow Airport. Now let's take a deeper look and uncover every layer of this story on our AI podcast.
I want you to imagine, just for a moment, that you are on a completely routine flight. It's just a standard, 90-minute hop from Dusseldorf to London.
Oh, yeah. A flight 100 people do every day without even thinking about it.
Exactly. You've probably got your headphones on. Maybe you're, staring out the window. You're descending over the city. The skyline is coming into view. And you can actually see the buildings around Canary Wharf getting closer.
Right. You're low. You're in the final stretch.
Yeah, you are at 4,000 feet. The landing gear is probably about to deploy. I mean, the flight is practically over. And then suddenly, with absolutely no warning, the aircraft just begins dropping from the sky.
It is, honestly, it's the ultimate nightmare scenario for any frequent flyer.
Totally.
Going from that absolute mundane routine to, well, a literal fight for survival in a matter of seconds. And you're suspended thousands of feet above a massively populated financial district.
It's terrifying. So welcome to this deep dive. Our mission today is to unpack the absolutely harrowing reports surrounding British Airways flight BA999. This all took place on July 6th, and we are going to decode the aviation data, explain the mechanics of exactly what went wrong up there in the skies over East London, and really explore the intense split-second human drama in the cockpit.
The human element is huge here, yeah.
It really is, because that drama ultimately saved the lives of around 180 people.
Yeah.
Okay, let's unpack this. We're looking at a British Airways Airbus A320. It's carrying a full load of passengers, right? And what started as a totally standard commute between Germany and the UK has now been classified by our industry sources as one of the country's most significant near-miss incidents in recent years.
Yeah, and when aviation authorities use a phrase like significant near miss, they aren't messing around. They were talking about margins of error that have essentially evaporated into nothing.
Just gone.
Right. This wasn't, a minor technical glitch causing a bumpy ride or something.
Yeah.
This was an event that pushed a modern commercial airliner, which is heavily reliant on millions of lines of computer code, mind you, right to the absolute edge of disaster.
And to really grasp how close they came to that edge, I mean, we have to talk about the invisible trigger that set this whole terrifying sequence in motion.
Mm-hmm.
Before we even get to the physical sensation of the plane plunging, we have to look at what was happening outside the cockpit windows, like on the nose of the plane itself.
Right, the external sensors.
Yeah, because the plane is over Canary Wharf, 4,000 feet up, in a totally critical descent phase, preparing to land at Heathrow. And that is when a piece of technology called the air data system just completely malfunctions.
And to understand the gravity of that failure, we kind of have to look at how a massive metal tube actually knows what it's doing up in the sky. I mean, the air data system is basically the sensory nervous system of the aircraft.
The sensory nervous system, I like that.
Yeah, it feeds essential performance data to both the human pilots and the flight computers. And honestly, the most critical piece of that data, especially during a descent, is the airspeed.
Wait, how does a plane actually feel how fast it's going? Because, in a car, the speedometer just measures the rotation of the tires on the actual road. But up in the sky, you aren't touching anything.
Right, you're in a fluid. And that is the brilliant and sometimes really vulnerable part of aviation engineering. An aircraft measures its speed through the air using something called pitot tubes.
Pitot tubes.
Yeah. If you look really closely at the nose of a commercial jet next time you fly, you'll see these small L-shaped metal probes sticking out.
Oh, I've seen those. They look kind of like little antennas.
Exactly. So as the plane flies forward, oncoming air, they call it ram air, rushes into those tubes. The system then compares the pressure of that incoming ram air against the static ambient air pressure outside the plane.
Okay, so it's taking two different pressures.
Right. And by calculating the difference between those two pressures, the flight computer can figure out exactly how fast the plane is physically moving through the air mass.
So it's essentially measuring, the force of the wind hitting it in the face to figure out its speed.
That is exactly the core mechanism, yeah.
Yeah.
But the vulnerability here is that these tiny physical probes are totally exposed to the elements. I mean, if they get blocked by ice, or if they get hit and damaged, or if the internal sensors that translate that pressure simply break down, well, the entire system just goes blind.
And the computers lose their grip on reality.
Exactly. Total disconnect.
I'm trying to picture the real-world danger of that for you listening. It's a lot like riding a bicycle, right? If you are pedaling really fast, it's totally effortless to stay upright. The speed kind of does the work for you.
Yeah, gyroscopic stability.
Right. But as you slow down to a crawl, like when you're approaching a stop sign, you start wobbling. The balance gets incredibly delicate. And if you are completely robbed of your sense of balance and your speedometer, right at that critical wobble speed, you wouldn't just keep rolling, you'd tip over.
Yeah, it captures the aerodynamic danger perfectly, actually. Because during the cruising phase of a flight, high up at 30,000 feet, you have plenty of speed and plenty of altitude. You have this massive buffer.
Margin for error.
Right. But when you are at 4,000 feet descending toward an airport, the pilots are intentionally slowing the aircraft down. They are bringing it closer and closer to the absolute minimum speed required to keep the wings generating lift.
Wow, so they are living in that wobble zone.
Very much so.
Yeah.
The margins for error during this phase are incredibly slim. You are maneuvering a massive machine in 3 dimensions, making these tiny calculated adjustments based almost entirely on the airspeed numbers on the dashboard.
So if those numbers disappear, or even worse, if they start feeding you false information, your reality inside the cockpit fundamentally disconnects from the actual physical reality outside the window.
It does. It's a terrifying scenario.
So when that data system fails, just how fast does a routine descent turn into a full-blown emergency?
Oh, it is nearly instantaneous. Literally, the moment you lose accurate airspeed data, the physical laws of aerodynamics basically start working in the dark. If the speed drops too low without the pilots or the computers realizing it, the airplane fundamentally stops flying and just starts falling.
And that falling is exactly what our reports say happened on flight BA999. The equipment failure led directly to a totally terrifying aerodynamic consequence, a stall. The plane stopped flying and started dropping right over London.
And what's fascinating here is how misunderstood the concept of a stall actually is in popular culture.
Oh, completely.
When most people hear the word stall, they immediately picture a car engine sputtering out and dying at a traffic light.
Yeah.
They imagine the plane's jet engines just went quiet, leaving it as this giant, helpless glider.
Right, and that's the danger of the car analogy, because in the air, the engines on that Airbus A320 could have been functioning flawlessly. Like they could be roaring at absolute full power.
Exactly. The engine thrust wasn't the issue at all. An aerodynamic stall happens when the wings themselves stop generating enough lift to support the immense weight of the plane.
The lift just dies.
Yeah, the dynamic force that's literally holding you up just evaporates.
So it's less like a car engine dying and more like a surfer who suddenly loses the wave and just drops into the trough. I mean, the water is still there, the surfboard is still functioning, your legs are working, but the dynamic force that was carrying you forward is just gone.
That's a great way to put it. The physics are identical. The reports highlight that a stall generally occurs for 2 reasons. Either the aircraft slowed down way too much, or it exceeded what we call the critical angle of attack.
Okay, I am stuck on this critical angle thing. I mean, I always assumed you just point the nose of the plane where you want to go. Why does pointing the nose up make you fall?
Okay, so think of the air as a fluid, right? The angle of attack is the angle between the wing of the aircraft and the oncoming air. To generate lift, especially at those slower speeds near landing, pilots will pitch the nose of the plane slightly up.
So the bottom of the wing catches more air.
Right, but if you pitch the nose up too high, if that angle becomes too steep, the air can no longer flow smoothly over the curved top of the wing.
Oh, I see.
The airflow essentially separates from the metal, it becomes turbulent, and the lift is instantly destroyed. And when that happens, gravity takes over immediately. The airplane rapidly loses altitude, and the flight controls become incredibly sluggish. They're just very difficult to manage.
But wait, aren't modern airliners designed with automated fail-safes to prevent this exact thing from happening? Because we are talking about a modern Airbus A320. These planes use fly-by-wire technology, right?
They do, yeah.
So the pilots aren't, like, pulling steel cables. They're sending electronic signals to a computer. Shouldn't a computer intervene and say, hey, we're going too slow, let's fix this, before a stall even has the chance to occur?
That cuts to the absolute heart of why this specific incident is so incredibly serious. You are entirely correct about fly-by-wire systems. Modern Airbus aircraft are packed with automated envelope protections.
Right, they're smart planes.
Very smart. And those protections are designed specifically to prevent stalls. But, and this is the big but, Those automated fail-safes are only as smart as the data they are being fed. We have to look back at that invisible trigger, the air data system malfunction.
Ah, right. The sensory nervous system is broken.
Exactly. The computers are suddenly blind. If the pitot-tubes or the sensors are feeding totally erroneous data to the flight computers, those fail-safes cannot protect you.
Wow.
In fact, it becomes actively dangerous. If the computer mistakenly believes the aircraft is flying too fast because of a faulty sensor, it might actually push the nose down to compensate.
Which you don't want at 4,000 feet.
No, you don't. And if it mistakenly thinks it's flying too slow, it might abruptly pitch the nose up, which inadvertently forces the aircraft into the exact stall it was designed to prevent. When the foundational data systems fail, the automated safety net just vanishes entirely. It's the classic computer science rule: garbage in, garbage out.
Wow. So when the computers are helpless or, like you said, actively making the situation way more dangerous, survival suddenly comes down entirely to the human beings sitting in the cockpit.
It does. It abruptly shifts from a highly automated monitoring job to a purely manual, highly dangerous recovery effort. You are no longer managing a computer system. You're physically wrestling a falling building.
And the reports give us this really chilling glimpse into exactly how that wrestling match played out in the cockpit of B899. Because according to the sources, the first officer initially attempted to manage this totally unexpected situation right after the instrument failure.
Which is standard procedure, usually.
Right, but as the aircraft's condition reportedly worsened, as the stall fully developed over London, the captain intervened directly. The captain literally took physical control of the aircraft to recover from the plunge.
And we have to emphasize, taking direct physical control from another pilot during a crisis is an incredibly extreme action in modern commercial aviation.
Walk us through the physical mechanics of that because, in a lot of older planes, the pilots share a big steering yoke between them, right? If one pulls, the other literally feels it. But the Airbus A320 is different, isn't it?
It's very different. In an Airbus, there is no shared central yoke. Each pilot has their own independent side stick. It's essentially a joystick located on the side console. The captain has one on the left, the first officer has one on the right.
Okay.
Usually, if both pilots try to move their sticks at the exact same time, the computer just averages their inputs out, which, as you can imagine, can be catastrophic in an emergency because their commands might just cancel each other out.
Oh, wow. So how does a captain actually take over if they can't just physically overpower a shared steering column? Like, how do you grab the wheel?
They have to use a physical override. There's a red button on the side stick called the priority takeover push button. To take control away from the first officer, the captain literally has to press and hold that red button to electronically lock out the first officer's joystick.
Just lock them completely out of the system.
Yes, while loudly announcing, "I have control."
Here's where it gets really interesting. I mean, think about the trust and hierarchy in your own workplace for a second. Imagine the sheer panic and the absolute terrifying certainty required to realize that your highly trained colleague is losing the fight. And you have to press a button to lock them out of the system because if you don't take over in the next split second, you are all going to die.
Yeah, that is not a procedural management decision. That is raw survival instinct. It is the ultimate override. I mean, in modern aviation, you have a pilot flying and a pilot monitoring. Both are highly, highly qualified professionals. For a captain to recognize that the situation is deteriorating so rapidly that they must actively, physically intervene and push their colleague out of the loop, I mean, that speaks to a level of imminent danger that investigators rarely see in commercial flights.
It's extreme.
And aviation specialists quoted in the reports use a very specific, chilling industry term to describe the risk level of this event. They stated that this situation carried the potential risk of hull loss.
Hull loss. It sounds, I don't know, so incredibly clinical for something so horrifying.
Well, the clinical nature of the term really masks an absolute catastrophe. Hull loss is defined as a situation where an aircraft is completely destroyed or damaged beyond economical repair.
Meaning it crashes?
Right. Means the aircraft impacts the ground, or structural forces just tear it apart in the sky. When aviation experts look at a flight data report and state that an incident carried the risk of hull loss, they are telling you, in polite industry terms, that this aircraft was mere seconds away from hitting the ground with everyone on board.
And they were dropping over Canary Wharf. I mean, one of the most heavily populated financial districts in East London. Just how narrow was the margin for survival before the aircraft was finally stabilized?
Well, while the reports don't give us the exact number of feet they lost in that initial plunge, We know that at an altitude of 4,000 feet, your margin for recovery is terrifyingly small.
Because there's just no room below you.
Exactly. A fully stalled commercial airliner can lose thousands of feet in a matter of seconds. The ground approach is incredibly fast. The fact that the aircraft recovered before impact, and, crucially, without structural damage from the massive G-forces of pulling out of the dive, is a huge testament to the aggressive speed of that captain's intervention.
Yeah, that split-second human intervention completely saved the day. I mean, the captain held that priority button, stabilized the aircraft, reestablished the lift we were talking about, and actually continued the approach.
Yeah, incredible flying.
The plane landed safely on the tarmac at Heathrow. No passengers were injured. Most of the people grabbing their overhead bags and walking off that plane into the terminal likely had absolutely no idea how close they just came to being a breaking news alert around the entire world.
It's wild to think about.
Yeah.
But, surviving the drop is really only half the battle for the aviation industry.
Right.
The immediate danger is over, sure, but now investigators have to meticulously reverse engineer the ghost in the machine to ensure it never happens again to another crew.
Yeah, and officially, this incident has now been classified as a loss of control in-flight event, or a LOCI. British Airways has confirmed they are cooperating fully, but they are, as you'd expect, remaining very tight-lipped, which is standard during an ongoing inquiry.
Right. And if we connect this to the bigger picture, this is where the Air Accidents Investigation Branch, the AAB, takes the reins. Their mandate isn't about placing blame or liability. It is purely about establishing the facts and finding the absolute root cause, and they are going to scrutinize every single millisecond of that 90-minute flight.
Well, and the incredible advantage investigators have here is that the plane didn't crash. Right, there is no charred wreckage to sort through in a field. They have the physical aircraft just sitting there on the tarmac.
Oh, that completely changes the dynamic of the investigation.
Huh.
They can pull the flight data recorder and cockpit voice recorder, the infamous black boxes.
Yeah, the data is intact.
Exactly. The flight data recorder logs hundreds of parameters multiple times a second. They will look at the exact telemetry of that air data system failure. They can pinpoint the exact fraction of a second. The pitot tubes stop sending accurate RAM air pressure data, and they'll see what erratic, chaotic numbers the computers were desperately trying to process.
So they can essentially plug that data into a simulator and perfectly recreate exactly what the dashboard looked like to the pilots and how the plane physically reacted in the air.
They will see every single input on those side sticks. But, the mechanical data is really only one piece of the puzzle here. They're also going deeply into the maintenance logs.
Right, looking for a history.
Yeah. Was there a known history of issues with these specific sensors? Was a scheduled inspection missed? And crucially, they're going to evaluate the human interface.
And this is where I really want to look at a detail mentioned in the sources, because the reports state that the captain involved, the one who pressed that priority button and took direct physical control to pull this massive jet out of a stall over London, has actually taken stress-related leave following the event.
Which is completely understandable.
Absolutely. But it's easy for investigators to look at the mechanical maintenance records, but how do they evaluate the human stress factor and split-second decision-making in these reports?
Yeah, evaluating human performance under extreme psychological duress is, without a doubt, one of the most complex challenges in any aviation investigation. Investigators will conduct extensive interviews with the crew. They are looking to determine the exact sequence of events, but more importantly, they're really trying to understand the human-machine interface.
How they interacted when things went wrong.
Right. When the air data system failed, how did the aircraft communicate that failure to the humans? Was the warning system clear and actionable? Or was the cockpit suddenly filled with just a confusing cacophony of alarms, flashing lights, and totally contradictory information?
Because if the computers are confused, the alarms they generate are probably just as confused, right?
Exactly the problem. The investigation will ask if the standard training the pilots received adequately prepared them to recognize and recover from a total sensor failure at 4,000 feet. The ultimate goal here is to determine if changes to airline procedures, simulator training, or the aircraft's warning systems are required to improve flight safety across the globe.
Basically, to make sure the next crew doesn't have to rely on a terrifying split-second override just to survive a routine descent.
Yeah. The entire modern aviation industry is built on a foundation of learning from these near misses. Every single close call is an opportunity to patch a hole in the safety net before a passenger slips through it. The final AAIB report will establish the precise mechanical cause of the event and evaluate the crew's response, which will give engineers and airlines a totally clear roadmap for what needs to change.
So what does this all mean? We started by asking you to picture a routine hour-and-a-half commute, a flight that hundreds of people take every single week. But beneath the surface of that mundane routine, this deep dive reveals both the incredible fragility and the immense resilience of modern aviation. We place our absolute trust in invisible technological safety nets, the pitot tubes measuring the wind, the computers calculating the angle of attack, the fly-by-wire envelope protections, just to keep us suspended in the sky. But when those invisible systems break down, when the sensors lie and the physics fail, the illusion of a routine commute completely vanishes. Survival suddenly comes down entirely to the immense hidden pressure placed on the human beings at the very front of the plane.
It really serves as a stark reminder of the duality of flying. I mean, it is a stunning miracle of modern engineering and automation, but it is ultimately safeguarded by raw human instinct and human courage. It really is. And I want to leave you with a final thought to mull over, building on exactly that dynamic between human and machine. As we push further into the 21st century, the aviation industry is heavily exploring AI-assisted flights and even fully autonomous commercial aircraft.
It's definitely coming.
Yeah, but an event like Flight BA912 makes you wonder, how do you actually code survival instinct into a computer? If a future autonomous system is being fed completely catastrophic, erroneous data by its own sensors, can an AI ever learn when to completely ignore its own internal logic to save a plane? Or is that split-second rebellion like the ability to look past the broken dashboard, feel the drop in your stomach, and just wrestle the plane back to the sky? Is that the one thing only a human being can do?
That is the ultimate frontier for automated safety. A computer follows the rules it's given, but surviving an unprecedented system failure often requires actually breaking the rules to find a solution. Whether code can ever replicate that kind of human intuition, well, it remains to be seen. A huge thank you to you for joining us on this deep dive. Stay curious, keep asking questions, and the next time you're on a routine flight looking out the window as you descend over a city, just take a moment to appreciate the incredibly complex dance of physics, technology, and human skill that is keeping you up there. We'll catch you on the next one.
Okay, one question for you. Do you think modern commercial aircraft rely too heavily on automated flight systems, or should airlines place even greater emphasis on manual flying skills to prepare pilots for unexpected emergencies like this one? Don't forget to comment it. Thanks.